Hello, and welcome to this Smiths Interconnect webinar. My name is Katie, and I will be your Global Spec moderator. Now let me introduce today's presenters and go over today's agenda. So with us today, we have Ron Douglas. He is the engineering manager at Smiths Interconnect. And we have Mike Schweier. He is a product line manager of filters and integrated filter assemblies. So gentlemen, welcome. And I'm going to briefly talk about our agenda today. So today we will discuss RF ceramic filter topology, including the overview of the ceramic filters. We're going to talk about understanding the advantages of ceramic resonator RF filters. We will be discovering the key design principles for ceramic RF filters and balance the trade-offs of performance, size, and weight. Following that, we will have a brief Q&A session. All right, so moving on, guys, I have a polling question I would like to put out to the audience to kick things off. So the question we're asking today, what is the single most important driving factor when you select an RF filter? So we have 4 options here for you: performance, size, cost, or lead time. So for our audience, if you want to go ahead and choose one of those options, we would appreciate your feedback. I'm going to leave the polling question up on the screen for about a minute to give everybody time to submit their answers. So again, the question is, what is the single most important driving factor when you're selecting an RF filter? So again, I'll leave that up there for a minute for all the attendees. If you guys could answer what's most important to you, your feedback is important to us. All right, guys, just a couple more seconds up on the screen here. And options are your performance, size, cost, and lead time. All right. Thank you, everyone from the audience who submitted an answer. I'm going to move us over to our results slide. And Mike, I'll pass it over to you to talk about our results today. It's looking like performance is our top contender here. So Mike, go right ahead.
Oh, thank you, Katie. Yes, performance is dominant response here, and that's a very good sign, because performance really enhances your system. So thank you for providing that feedback. Okay. Again, I want to thank you, Katie. We are excited to talk to everyone today about ceramic resonator RF filters. In today's webinar, we will be discussing the applications for ceramic filters, the theory of the design techniques for ceramic filters, and the characteristics of these filters. RF filters are used to modify signals to remove interfering frequencies that distort or diminish RF energy in multiple applications. Examples include communication systems where an antenna would receive signals at multiple frequencies around the carrier frequency. To enhance the range and performance of the communication system, an RF filter selected around the center frequency and bandwidth of the carrier signal would be utilized. There are many factors to consider when choosing the appropriate RF filter for an application. The frequency range, fractional bandwidth, the filter transitions from the pass band to the stop band, and the power level of the signal are some of the variables to consider. Additionally, the performance of the filter, the loss of the passband and the amount of rejection, the size and cost are other variables. Often, the filter selection will balance the trade-offs with smaller size and weight and the filter performance. The ceramic resonator filter is a very good topology for excellent performance in small size and weight. These filters are available to support frequency ranges from 400 megahertz to 6 gigahertz. Ceramic filters were first introduced about 80 years ago and have emerged as strong candidates for filter solutions due to their excellent performance, small size, and low cost. The filters are comprised of high Q, high dielectric constant ceramic resonators, which are capacitively coupled and are typically connected to a surface mountable printed wiring board. The ceramic resonators are silver plated and also boast low temperature drift. The high relative dielectric constant allows for smaller size filter options, while the high Q available supports the low loss and high rejection these filters offer. My colleague Ron will get into more details on the filter theory a little later in the webinar. Ceramic filters are used in commercial, defense, and space markets. Design and manufacturing techniques are employed to optimize these filters for these different markets. For example, applications which require these filters to be exposed to condensing humidity would require the packaging to be hermetic, as condensing humidity would degrade the filter response. These filters are suitable for harsh environments and are able to withstand high vibration and shock conditions. These filters have been successfully qualified for many of the environmental and physical characteristic tests per MIL Standard 202. They are well suited to support RoHS and REACH requirements as well. I will now turn the webinar over to Ron, who will provide an in-depth review of the ceramic filters.
Thanks, Mike. Over the next few slides, I hope to cover an overview of ceramic filters, point out some of the largest advantages, walk through a basic design flow, and finally discuss key trade-offs. Ceramic filters are an excellent choice for RF designers as the perfect moderator between other topologies. While offering lower cost and better performance than most discrete solutions in the same frequency range, they actually maintain the same or even smaller footprint. They will not be able to compete with the performance of a high-Q cavity solution. However, they will be a fraction of the size. And while printed filters command attention today by their incredibly small envelope, ceramic filters will still offer better performance generally at a similar price and quantities. We will go into further detail a bit later, but I wanted to set the tone for why this topology is an excellent in-between quote-unquote solution when performance, price, and size are all important to the customer. Now to speak to where this topology fits and works. Ceramic filters tend to operate best when used between the UHF and C bands. Most solutions are indeed surface mount technology, but we can offer custom-made solutions as coaxial and RF outputs as well as hermetic packaging, as Mike alluded to. From this slide, we can see that ceramic resonators are available in various sizes to allow the designer to work at various frequencies. For each of these sizes, there are even numerous dielectrics available to allow further control over the overall footprint. Looking at this visual comparison, we quickly see the relationship between size, frequency, and quality factor, or Q, as we'll speak to, which we'll be speaking about in coming slides. Generally, the higher the frequency, the smaller the resonator, the lower the Q performance, generally. Now let's consider a single 4mm ceramic resonator at 800 megahertz with a dielectric constant of, let's say, 21. The electric length will begin approximately 83 degrees and yield a physical length of approximately 18.8 millimeters. We can view the CDA model of the resonator to the left. The model is defined by the inner and outer dimensions, the length, and the dielectric. We refer to the performance of the resonator or resonance section by its quality factor, or Q, as I said earlier. This is simply the ratio of the stored energy in the resonator to the energy dissipated in the resonator. The quality factor is inversely proportional to its insertion loss. While the full calculation is mathematically involved, well-established curves provide a multiplication factor for a given dielectric and its size. In our example, we expect a transmission Q of nearly 280. We now move to the advantages of using ceramic topology. First, we will compare a ceramic solution with a discrete solution. Working at the same frequency of 800 megahertz, let us now consider a 3-section bandpass filter solution in both discrete elements as well as ceramic resonators. Looking at overlaid solutions with a 3 dB bandwidth of, say, 50 megahertz, we clearly see the insertion loss or the performance of the ceramic solution outperforms the discrete solution by roughly 1 dB. This is due to the quality factor, or Q, of the ceramic resonator being much higher than the Q of the inductor or capacitor in the resonant circuit in the same discrete solution. Now let's consider a loaded or tuned ceramic resonator from the previous example of 18.8 millimeters. If we were to lay this side by side to a tuned brass resonator for a cavity solution and a dielectric of air or dielectric of 1, The physical length difference is obvious. The brass resonator is more than 4 times the length to achieve the same resonant frequency. So here, the ceramic is smaller. Next, we will look at a simple design approach to using ceramic resonators. All designs begin with a request for quotation in some form or another, the 3 main variables being, for any design approach, performance, size, and cost. Experience shows that the rating for each of these will vary from customer to customer based on a specific set of requirements. But as our poll question showed, in most cases, performance sits at the top. One of the tools we offer our customers to help with identifying a solution quickly is Filter Select, a link to which will be provided at the end of the presentation. This is an online tool that allows the customer to input parameters based on their needs and have a solution output in the form of a data sheet with a part number, expected specifications, S2P performance plots, and a mechanical outline. Keeping consistent with the presentation, let's input 800 megahertz as the center frequency, 50 megahertz for the 3 dB bandwidth, and we will also define the solution by selecting an attenuation of 40 dB at, let's say, 650 megahertz. The application then yields a ceramic solution 3DF4-800/50-M. This is a Smith's interconnect number, which is a descriptive part number, which appears in the final quote as the top-level assembly. Reading left to right, we interpret this as 3 sections, dielectric filter using 4 millimeter resonators, 800 megahertz center frequency, 50 megahertz 3 dB bandwidth, and finally SMT format. Using 2D synthesis tools such as Keysight's Pathwave or others, we are able to build the model in a workspace and optimize the variables to generate the optimum values for the circuit. Once the electrical design is completed and physical component part numbers are selected and assigned to a bill of material, a Rev1 assembly drawing is created. But before this, we then visualize the output performance using S parameters and review the insertion loss, S21 against S11, reflected against the required specification using masks. After the bill of material is created, we then begin to generate the visual assembly. We will see a simple assembly right now consisting of a carrier board, actual 3 ceramic resonators, the coupling structure, the connecting tabs, silver jumper wires, a cover, and finally a label. The BOM and the router will also direct the assembler in what alloys to use and where to solder the assembly together. Finally, we will look at the trade-offs when selecting a ceramic topology over a discrete, cavity, or even planar filter. One of the observations one might make after viewing the previous assembly is how few parts there are in a basic ceramic assembly. This is one of the characteristics that allows ceramics to generally be more cost-effective than discrete or cavity solutions. Discrete assembly demands more skilled artisan labor, while cavity solutions demand more CAD and CAM resources for machining, as well as the raw material. The ceramic topology will generally outperform discrete solutions in the same frequency range due to the higher Q, as we saw during our discussion of advantages. While cavity solutions will generally outperform ceramic solutions, we have seen that at the same frequency, the cavity solution will be much larger. So here, the ceramic has the advantage of physically smaller size. Planar filters certainly command the advantage of the smallest footprint for a given frequency, but their performance will generally be less than the ceramic solutions at a given frequency due to their limited quality factor, or Q. And finally, I want to review what we have covered in this session. We have looked at an overview of ceramic resonators and their use in RF solutions. We've discussed the advantages when comparing to other topologies. We have looked at a simple design process flow for a given ceramic solution from quote to basic assembly. We have also looked at the trade-offs when comparing 4 topologies side by side. To the right of the slide, we are sharing the link to our Filter Select tool to assist you as designers in selecting the best filter and topology for your needs. We welcome any feedback, both positive and critical, to help us to continue improvement on this resource. Finally, I want to thank you for your time today and attention. I will now turn this back over to our PLM, Mike Schweier.
Thank you, Ron. I will now just take a few minutes. I'm sorry. I will now just take a few minutes to summarize our total filter capabilities. We offer full design services from EM simulation to work and prototype for products that are suitable for applications in the aerospace, commercial, and military markets. We support custom solutions and custom test requirements, and as we just discussed, many of our filter solutions promote the reduced size, weight, and power. We have several filter design options, such as the Planar X series, which, as Ron stated, can offer a very small footprint. We have standard bandpass and low-pass Planar X filter families, and we do offer custom solutions for frequencies up to the Ka band. We discussed the ceramic resonators filters thoroughly today as one of the topologies. We have RF tunable filters that are available from 24 megahertz to 3000 megahertz with full octave tuning. Our discrete filters are available from 5 megahertz up to around 10 gigahertz, and they offer a lot of flexibility with fractional bandwidth and filter configuration. Finally, we support high-performance cavity and waveguide filters, which are optimal for high-power applications and provide the lowest insertion loss and best filter transitions. I would like to thank everyone for attending, and now I'll turn this back over to our moderator, Katie.
All right. Gentlemen, thank you so much for that great presentation. So we do have time now for some questions from our audience. Let's see what we have for questions now, gentlemen. So this one here, what type of power can ceramic filters handle?
Oh, thank you, Katie. I'll take that question. We've recently tested our ceramic filters up to 16-watt continuous, and that was this year. So it depends on a few different factors, but they can handle some pretty good power. And like I said, we were successful up to 16 watts continuous.
All right, great. Thank you, Mike, so much for that answer. All right, we're getting a couple of questions in our queue here, so let me find our next one. For anyone that's watching also and you want to fill out a survey for us to give us a little feedback from today, that survey is located along the bottom of your attendee console in the survey widget. So feel free to grab that and fill it out if you don't mind. Your feedback is always important to us. Okay. Our next question here. Can ceramic filter designs be combined with other filter design techniques, such as discrete designs?
I'll take that, Katie. Yeah, absolutely. We don't show it in the slides today, but many times we can combine most of these topologies. We can combine together to take advantage of the strengths of each of these topologies together. So many times we can take a ceramic and then marry it up with a discrete or cavity. It can be done.
All right, great. Thank you so much for that answer. Okay, looking at our queue here, we've got time for a couple more questions. And if we don't have time for your question today, do not worry. We will reach out to you following today's webinar. All right, gentlemen, our next one here. What is a typical lead time for a cavity filter?
I'll answer that, Kitty. We have some variables that go into it, but our typical lead time is 8 weeks from the required specifications until we get some prototypes out.
All right. Thank you so much for that answer. So we're going to give everybody another minute or two to type in any last minute questions that they have. And if you do not hear your question being answered, don't worry. We will reach out to you following today's webinar. So gentlemen, let's see if we get any other ones in here in our queue. So we'll just give everybody a second. All right, our next question here, guys. Performance may be important, but how does cost, lead time, and availability compare to other solutions?
I can take that one, Mike, on that. So basically, one of the advantages, this is actually where the ceramics can shine, is because the other solutions, we're aggressively right now, Smiths Interconnect is offering an 8-week lead time currently on NPI product as well as legacy. But with that, the ceramics have the advantage of, as you've seen, it's a very smaller bill of material. Most everything that you saw there is stocked for us. And so where you use a discrete, you can have a stock housing and pins and such, but you still have to build the circuit, and there's a lot more detail that goes into generally most discrete circuits. Whereas a cavity, you not only need the CAD time and you have to machine the metal and form it around it, the ceramics are usually put together. The work is really just done at the design stage, and the assembly follows the same one. So of the topologies, it lends itself to be one of the quickest lead times.
All right, great. Thank you so much for that answer. So I'll give the attendees about another 15 or 30 seconds just to type in any last minute questions if you have any. If not, then we're going to wrap the webinar up right there, but we will give everybody another second or two to see if we have any last minute questions coming in, guys. And then just a reminder to grab those resources on your way out today. So it looks like that's all the questions that we're going to take for today. Reminder to the attendees, if you do have any questions that come up after today's webinar is over, you can come back during our on-demand period and ask any questions that you have at that time. So, gentlemen, I'm going to start to wrap the webinar up right now. I want to say a huge thank you to Ron and Mike for a great presentation and for answering a couple of our attendees' questions. So, gentlemen, thank you both so much for being here.
Thank you, Katie, and thanks for everyone for attending. I enjoyed presenting this today.
All right. Thank you guys so much. And for our audience members, so I want to say thank you for taking time to attend this webinar event, everybody. Take care, and we will speak with all of you soon.